reality is not as solid as it seems. Beneath the surface of what we call existence lies an intricate web of rules, so strange and counterintuitive that they defy the very logic we rely on. Imagine a world where information isn't just something we store on hard drives, but a fundamental building block of reality itself, where bits of data are not fixed ones and zeros, but fluid, shifting entities existing in multiple states at once. In this realm, observation changes the very nature of existence. Here, two particles, separated by galaxies, can be so deeply connected that the actions of one instantly affect the other, where a simple measurement can erase possibilities, collapsing the limitless into the defined. This isn't the realm of science fiction. It's the foundation of the universe itself. For centuries, classical physics painted a world of predictable order, but as we probe deeper, cracks began to form. The smallest scales of nature do not behave as our instincts tell us they should. Instead, they operate on principles so bizarre that even Einstein himself struggled to accept them. What if information isn't just an abstract concept, but the scaffolding upon which reality is built, a cosmic algorithm processing the fabric of existence? Yet, for all its mystery, quantum information is not just a theoretical curiosity. It holds the potential to revolutionize technology, from unbreakable encryption to computers that defy the limits of classical logic. But could it also hold answers to questions even more profound? Could the nature of reality itself be, at its core, an elaborate interplay of quantum codes? The deeper we look, the stranger it becomes. The quantum world is a realm where conventional intuition crumbles, and with it, our understanding of something as seemingly straightforward as information undergoes a profound transformation. Information, which classical physics views as an abstract concept, bits stored on drives or written on paper, takes on a physical identity in the quantum domain. This physicality changes the very way we define and process information. Imagine if a coin, instead of landing on heads or tails, spun forever in a ghostly blur of both outcomes. That is the strange reality of qubits. This non-binary nature adds remarkable complexity and power to the notion of information itself. Consider, for instance, how quantum mechanics challenges the deterministic perspective of classical physics. Classical systems, like a coin flip, are predictable if you have enough data. Quantum systems, however, demand more than just data. They demand a reevaluation of how we interact with the universe itself. This is where information becomes more than a record of reality. It transforms into something actively woven into the fabric of quantum mechanics. At its core, the theory suggests that all physical systems carry information. But it is not merely descriptive. Quantum information has inherent properties that set it apart, enabling certain transformations possible in no classical counterpart. Take the concept of measurement, for example. What happens when you look at a quantum system? This question strikes at the heart of the measurement problem, one of quantum mechanics' most debated puzzles. Until observed, a quantum particle is like an unread book. Every possible story exists at once. The moment we measure it, we choose a single narrative. But does this act represent the creation of information, or are we merely revealing a pre-existing reality? The paradox deepens when you consider quantum states, which cannot be fully known without destroying them. Unlike classical states, where observation has no inherent cost, quantum information defies this expectation. Quantum measurement also forces us to rethink the concept of truth. Imagine two scientists trying to understand a system state. Each measures from a different angle and draws distinct conclusions. Unfortunately, neither entirely grasps the complete picture because quantum mechanics forbids full certainty. The complementary nature of quantum systems ensures that knowing one property requires sacrificing certainty about another. This principle isn't a mere artifact of our limitations, it's built into reality. From uncertainty, we move to an even stranger quantum feature, entanglement. When two particles become entangled, their states are no longer independent. Instead, they form a single shared state, regardless of the distance separating them. Einstein dismissed it as an eerie coincidence, yet today, we know entanglement binds particles like invisible threads stretching across the cosmos. Through entanglement, one particle knows the state of its partner instantly, no matter how far apart they are. The implications of quantum entanglement for information transfer are profound. For instance, quantum teleportation isn't science fiction anymore. When two particles are entangled, information about their states can be effectively teleported across space without physically moving any matter. Though no faster than light travel occurs, it respects the limits of relativity. The phenomenon redefines how we think about communication. But limits remain. Quantum mechanics also imposes strict boundaries on information. The no-cloning theorem states that quantum information cannot be copied perfectly. This ensures that quantum reality holds onto its secrets. You can't simply duplicate a quantum state. Entangled pairs themselves come with their own measure of informational complexity via entanglement entropy, a quantity representing the shared data between particles. This entropy explains why, despite entanglement's potential for teleportation, it does not allow free, unlimited communication. Underlying all these principles is the uncertainty principle, Heisenberg's revolutionary assertion that not all properties of a particle can be precisely known simultaneously. If you pinpoint a particle's position with extreme accuracy, its momentum becomes uncertain, and vice versa. This places a cap on how much usable information any quantum system can offer at a given time. Encoding and retrieving data in this framework requires deliberate trade-offs, a kind of balancing act dictated by the system's fundamental limits. The complementarity principle further enforces the idea of trade-offs. One observation trades off for another, with information about one domain costing you clarity in others. This principle challenges classical mechanics, where perfect knowledge seems theoretically attainable. Here, the knowledge is inherently incomplete by design. All this complexity raises deeper questions about the role of information in the universe itself. Is reality, at its core, informational? What if the universe is a quantum computation processing information on a cosmic level? This isn't just abstract speculation. Decoherence, the process by which quantum possibilities reduce to classical certainty, might serve as a bridge. Decoherence allows quantum states to seemingly lose their mystery, forming the classical bits of data we're used to. It's through this bridge that classical information derives from quantum origins. The idea of quantum information suggests that our universe might not simply obey physical laws, it might embody them as computations. Quantum mechanics suggests that information plays a foundational role in the structure of reality, possibly encoding the rules that govern its evolution. This transcends the classical idea of systems composed of particles. Instead, it imagines particles as carriers of quantum information, data packets navigating a computational structure. While this paints a picture of quantum reality, it also has practical applications, particularly in cryptography. Quantum data underpins the most advanced security protocols ever devised. Quantum mechanics offers a framework for secure communication, where entanglement-based protocols ensure the integrity of transmitted data. The randomness inherent in quantum mechanics provides a foundation for secure encryption protocols far beyond the reach of classical computers. Indeed, quantum randomness lends unpredictability, an advantage in fields requiring utmost security. Looking ahead, the quantum internet could revolutionize secure communication at a global scale. Imagine an interconnected network that uses quantum mechanics to enable unbreakable encryption, safe from the computation power of any future supercomputer. Across both theory and application, quantum information emerges as a key to reshaping modern understanding, not just for scientists pondering the mysteries of the universe, but for practical, real-world uses fueling progress. Fundamental quantum knowledge reshapes our deepest understanding of reality. It ties together concepts like measurement, uncertainty, and entanglement and reimagines them as constituent parts of a single framework. This framework doesn't just describe reality, it actively determines it. From securing communications to pondering the nature of existence itself, quantum information shifts our perspective in profound ways. Could this be the foundation of reality? Or merely a window into an even deeper layer, awaiting discovery? The tantalizing potential ensures one thing: this quantum narrative is far from over. From entropy and thermodynamics to the deepest mysteries of quantum mechanics, information serves as a crucial counterpart, threading its way through the varied phenomena that define the physical world. To understand how profound this concept is, one must first consider the relationship between information and entropy, a topic central to the second law of thermodynamics. From the gradual crumbling of mountains to the fading memories in our minds, entropy is the universe's way of ensuring that order is never permanent. But here's where information comes into play. Information, in its purest sense, is about reducing uncertainty. When an event occurs or a system is observed, the information gained reduces entropy locally, even as the universe's overall entropy continues to increase. This dance of disorder and information is beautifully illustrated in Claude Shannon's groundbreaking information theory. Shannon's work mathematically connects entropy and information, unraveling how the reduction of uncertainty is itself a transfer of order into otherwise chaotic systems. Further deepening this interplay between information and physical laws is Rolf Landauer's principle, which links computation, the erasure of data, with heat and energy exchange. According to Landauer, erasing a single bit of information from a computer has a physical cost. It generates a small but inevitable amount of heat. This principle established that computation isn't abstract. It's bound by the same thermodynamic laws that define energy and entropy. Intriguingly, this ties computation to the material universe's physical processes, merging the metaphysical concept of information with tangible consequences. Consider how this relationship manifests in classical physics. One of the most famous paradoxes addressing information and thermodynamics is Maxwell's demon. Imagine a tiny creature capable of sorting fast and slow-moving gas molecules, like some omniscient gatekeeper. The demon seems capable of decreasing entropy in a closed system, which would apparently violate the second law of thermodynamics. However, upon closer analysis, physicists realized that the demon's act of gathering and processing information generates entropy, thus preserving the overall balance. This thought experiment demonstrates how inseparable information is from the physical processes it observes, and how it tempers the behavior of apparently chaotic systems. Information's role extends further when viewed alongside relativity. The transfer of information is restricted by the speed of light, a limit safeguarding the principle of causality, cause always preceding effect. This speed constraint ensures that no violation of temporal order can occur, embedding information flow into the framework of space-time itself. Meanwhile, the black hole information paradox challenges whether information is permanently lost when matter is consumed by a black hole. Since entropy and information are so closely tied, this paradox raises profound questions about how physical laws reconcile quantum mechanics with gravity. Beyond classical physics, thermodynamics, and relativity, we must venture into the dynamic world of self-organization and cosmic evolution to fully appreciate the role of information. Despite the universe's steady drift toward greater entropy, astonishingly intricate structures continuously emerge, from galaxies and stars to living organisms. These systems form through a process known as self-organization, where the flow of energy and information guides particles, molecules, or celestial bodies into complex, ordered states. Information becomes the silent architect of advanced systems, building higher forms of order against the relentless tide of universal chaos. This dynamic is perhaps best understood through the concept of Boltzmann's entropy formula, which interprets entropy from a statistical perspective. Think of a deck of shuffled cards. Disorder arises because there are countless ways the deck can remain disorganized, but only one precise arrangement to organize them in numerical order. Information can move the system toward that singular ordered state. Scaling this idea to the universe, local reductions in entropy, like star formation or biological evolution, are achieved through flows of energy combined with informational processes that carve intricate complexity within an open system. Here's where the arrow of time comes into play. We distinguish the past from the future because time's forward passage correlates with increased entropy. However, localized complexity seems to defy this principle, suggesting there's more happening beneath the surface. Life, for instance, thrives by increasing local organization through energy absorption. Plants use sunlight to assemble themselves at the molecular level. At the heart of these processes lies information, encoded within DNA directing life's remarkable order against entropic dissolution. The same principles of information shaping order apply within the realms of quantum mechanics and measurement. At the smallest scales, extracting information from a quantum system invariably changes the state of that system, embedding the act of observation into the physical outcomes being observed. This is the basis of the thermodynamics of measurement, illustrating how retrieving information about a particle's spin, position, or energy alters its quantum state. Decoherence, another process central to quantum theory, turns potentially contradictory quantum states into classical-like behavior by encoding quantum information in the environment. Such mechanisms anchor the macroscopic world we experience. Perhaps one of the most forward-looking applications of information resides in quantum computation, where information is processed at unprecedented scales and speeds. Unlike classical computers analyzing one logical process at a time, quantum computers explore multiple possibilities simultaneously, owing to the principle of superposition. This capacity enhances computing power exponentially, paving the way for breakthroughs across science, engineering, and artificial intelligence. Looking ahead, the frontier of information physics hints at radical insights. Some researchers propose that the principle governing quantum gravity, one of physics' greatest unresolved puzzles, may be derived from informational constructs. The holographic principle, for instance, theorizes that the entirety of a three-dimensional space can be described by the information encoded on its two-dimensional boundary. If this is true, information may not just govern physical processes, but constitute the very essence of reality itself. Further advancements in information-based thermodynamics promise benefits beyond conceptual breakthroughs. Imagine dramatically energy-efficient systems leveraging principles like Landauer's, a future where computation, communication, and even everyday energy use are guided not by raw consumption, but by information flow, vastly reducing their environmental impact. Though this video explored the synergy between information and physical laws, one overarching question remains tantalizingly unanswered. What if the universe itself is fundamentally a vast, interconnected field of information? If so, every star, planet, and living being would form a constituent of a grand informational matrix extending across space-time. Understanding this deeper reality might unlock not only technological revolutions, but also reveal our place in the intricate dance of order, chaos, and knowledge. Information, once viewed as mere data, now emerges as the very scaffolding upon which the universe is built. From entropy to self-organization, from quantum systems to cosmic evolution, it illuminates paths toward understanding what energy and matter alone could not explain. As we continue probing the mysteries of information and its physical manifestations, one thing becomes clear. It's not just about what the universe is made of, but what it communicates. With information, the cosmos organizes, evolves, and ultimately tells its story. Life, at its very essence, can be seen as a sophisticated information processing system. Every cell in your body operates like a biological computer, handling vast amounts of information to sustain life. DNA is not just a molecule. It is nature's own programming language, a biological script written over billions of years. This molecule encodes the instructions that power and regulate your cells, guiding everything from cell division to protein synthesis. Think of it as a library of life, where every book is a gene containing chapter after chapter of evolutionary wisdom accumulated over billions of years. Evolution itself can be understood as the editing and refinement of this library. By introducing variations in genetic information, through mutations, recombinations, and even external influences like epigenetics, life experiments with new editions of its chapters. Mutations act like trial edits, altering the information slightly. Natural selection, in turn, acts as the harsh editor, preserving the most useful variations and discarding those that don't quite fit the narrative of survival. This process, repeated across countless generations, is not just random chaos, but an optimization of the information that sustains life. These principles are deeply rooted in information theory, a field initially designed to study how computers transmit data. Surprisingly, the rules of information fidelity, redundancy, and error correction also apply to our genetic code. DNA, for instance, is brimming with built-in safety mechanisms. Specific sequences can correct errors in replication, ensuring that vital instructions survive despite the tumult of cellular processes. Yet, this redundancy doesn't stop evolution. Rather, it enables life to adapt by providing a stable foundation upon which variations can occur. Consider how evolution mirrors an optimization process when looked at through this lens. Over time, life selects and amplifies beneficial genetic information while discarding inefficient or harmful variations. Even non-coding DNA, once thought to serve no purpose, plays integral roles in regulation and expression. It's no longer just about the coded message of life, but the broader framework of biological information that dictates functionality and survival. The story of life's information continues in the intricate cellular networks that govern living organisms. Information transfer within cells is akin to a symphony of signals. From DNA transcription into RNA to the translation of RNA into proteins, these steps represent the flow of biological information in remarkable precision. Proteins, the end products of this flow, serve as the functional machinery of life. Interestingly, the way cells process this data is decentralized, much like distributed computing, enabling them to operate efficiently in a constantly changing environment. The role of information in building evolutionary complexity is especially captivating when one examines multicellular organisms. The leap from single-cell life to multicellular arrangements required an ingenious restructuring of how information is stored, processed, and transmitted. These creatures had to find new ways to coordinate functions across billions of interconnected cells. The emergence of neural networks in highly evolved species, for example, added an advanced layer akin to a supercomputer, dedicated to processing sensory input, driving behavior, and fostering decision-making. On the other end, bacteria adopted horizontal gene transfer, an almost hacker-like capability to exchange genetic information beyond traditional inheritance. These mechanisms underscore varying strategies life uses to handle the complexities of evolutionary adaptation. Adaptation itself, at its core, revolves around changes in how information is processed. Organisms constantly adjust their internal and external information strategies to respond to environmental pressures. For instance, memory and learning in species like birds or mammals showcase adaptive mechanisms that refine how they store and use information to make decisions. Environmental stressors act as feedback loops that shape these processes, forcing life to operate like a series of computations that maximize efficiency. The influence of information becomes even more fascinating when we consider how evolutionary processes extend beyond biology. Take communication and cognition in higher organisms. The evolution of language in humans, for instance, isn't just the development of sounds and words. It represents a leap in information storage and exchange, allowing knowledge to accumulate across generations. Language is, in many ways, externalized biological information shared and built upon in ways that genetic data cannot yet rival. Over time, human culture and technological advancements have extended the principles of biological information processing into artificial systems, from writing to the computational marvels we use daily. Even intelligence itself is deeply tied to how organisms process and utilize information. The increased complexity in neural connections among intelligent species reflects the growing need to analyze, store, and respond to enormous amounts of data. Human cognition, and by extension, intelligence, has co-evolved with these information processing abilities. Simply put, intelligence is not just about being able to think. It's about how efficiently information can be acquired, analyzed, and translated into action. Understanding these connections between biology, information theory, and evolution paints a compelling portrait of life. It's a narrative of constant change, refinement, and adaptation, where information lies at the heart of everything. Life evolves, not randomly, but systematically, finding new ways to process, store, and leverage its informational wealth to thrive against the odds. Evolutionary changes didn't just grant life the ability to survive. They built adaptations like communication and cognition that extend far beyond biometric functions. Today, human technology mimics life's computational efficiency, continuing the evolutionary process in the digital realm. Evolution is, then, not just the survival of the fittest, but the survival of the most efficient at handling information. And while we've only scratched the surface of this fascinating interplay, one thing is clear. Life isn't just a series of chemical reactions or genetic codes. It's an endlessly unfolding story of information. From genetic code to artificial intelligence, this flow proves central to our understanding of life and the universe. If you've made it this far, perhaps you're someone who sees the world as a web of interconnected ideas waiting to be decoded. And who knows? Maybe the next great leap in our understanding of information and evolution lies in your hands or your mind. Explore further and see how the story evolves. This isn't just a theoretical curiosity, but an experimentally verified reality. Particles can share a relationship so profound and immediate that it seems to challenge the notion of locality, the idea that objects can only influence their immediate surroundings. But here's where things get even stranger. This concept is so counterintuitive that Albert Einstein famously labeled it spooky action at a distance. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, constructed the EPR paradox to illustrate the uncomfortable implications of entanglement. They argued that if quantum mechanics were right, then particles could seemingly communicate faster than the speed of light, a clear violation of relativity. To Einstein, this suggested that quantum theory was incomplete and that hidden variables must exist to preserve the integrity of locality. Enter Bell's theorem, a mathematical dagger to the heart of hidden variable theories. Physicist John Bell formulated inequalities that tested whether the predictions of quantum mechanics could be explained by any local hidden variable theory. The verdict? Experiments have overwhelmingly violated these inequalities, affirming that quantum mechanics is correct in its non-local predictions. What these experiments revealed was not just perplexing, but revolutionary. Quantum linkage is a tangible phenomenon, transcending classical limitations. But how does this happen? The answer lies in quantum measurement. When we observe or measure an entangled particle, its state collapses, determining its properties instantly. And this action, this mere act of measurement, affects its entangled partner at the exact same moment. This phenomenon, known as wave function collapse, raises profound questions about the role of the observer in defining reality. Is the universe fundamentally deterministic, or does observation shape its outcomes? This brings us to the concept of decoherence, which helps bridge the gap between the quantum and classical worlds. Decoherence explains how quantum superpositions seemingly vanish when observed, leading us to perceive a stable classical reality. Yet, it does not answer the ultimate question of what reality truly is, a mystery that keeps physicists up at night. Different interpretations of quantum mechanics wrestle with this riddle. The Copenhagen interpretation, for example, suggests that observation collapses probabilities into reality. The many worlds interpretation, on the other hand, posits that all possible outcomes occur in parallel universes, leaving us to observe just one branch of an endless multiverse. The profound implications of quantum linkage extend beyond theory into revolutionary technology. Take quantum cryptography, for instance, where entanglement ensures secure communication through quantum key distribution. By leveraging entangled particles, QKD can detect any eavesdropping attempts, making it virtually unhackable. Similarly, quantum teleportation utilizes entanglement to transfer quantum states instantaneously, a feat that could revolutionize data transmission. The same principles drive the advent of quantum computing. Unlike classical computers, which process bits as 0s or 1s, quantum computers use qubits that can exist in multiple states simultaneously. This parallelism enables them to perform complex calculations at unprecedented speeds. The unseen quantum bond enables qubits to work in harmony, unlocking unparalleled computational power, promising breakthroughs in fields from pharmaceutical research to financial modeling. But what if entanglement isn't just a quirk of the quantum realm? Some physicists speculate that it might be woven into the very fabric of space-time. The ER equals EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a deep connection between quantum entanglement and wormholes, formerly known as Einstein-Rosen bridges. This provocative idea posits that the entanglement of particles could correspond to microscopic wormholes connecting them. If true, it might imply that the universe is a vast web of quantum connections, linking not just particles, but perhaps galaxies, dimensions, and even realities. This hypothesis bridges two of physics' most breathtaking disciplines, quantum mechanics and general relativity. While the former governs the subatomic world and the latter describes the cosmos on a grand scale, their unification has long eluded scientists. Could entanglement be the missing piece? If space-time itself is an emergent phenomenon arising from quantum processes, then entanglement might hold the keys to understanding the ultimate nature of reality. The implications stretch beyond science into philosophy, ethics, and even our everyday lives. If entanglement challenges classical notions of locality and objectivity, what does that say about our interconnectedness as human beings? What if our actions ripple through an invisible web, influencing others in ways we can't even detect? While these are speculative musings, they underline the profound interconnectedness that entanglement symbolizes, not just in physics, but in existence itself. Imagine a future where entanglement isn't just a topic for laboratories and lectures, but a practical pillar of everyday life. Your sensitive data is transmitted securely through quantum encrypted networks. Quantum computers solve problems in moments that would take classical systems millennia. Medical researchers crack the codes of genetic diseases using calculations too complex for today's technologies. Space exploration advances to unimaginable heights as entanglement unveils the secrets of space-time travel. And yet, for all its promise, entanglement reminds us that the universe retains its mysteries. It challenges our notions of causality, of distance, and of reality itself. It urges us to rethink our place in a cosmos where the boundaries between here and there, now and then, blur in the face of quantum interconnectedness. What we've uncovered so far is merely the tip of the iceberg. With each experiment and theorem, entanglement continues to provoke, puzzle, and inspire. It invites us, not just as scientists, but as curious beings, to look closer, think deeper, and imagine further. If this tantalizing glimpse into quantum reality leaves you yearning for more, there's a hidden web of knowledge waiting to be explored. Because when it comes to understanding our universe, the adventure is just beginning. The universe is a sprawling enigma, captivating humanity's greatest thinkers for centuries. For centuries, we've observed its patterns, dissected its laws, and theorized its origins. But what if we told you that the very fabric of reality itself could be understood in a radically innovative way, as if the universe operates like a colossal quantum computer? Prepare to challenge your perceptions of existence as we explore how quantum mechanics underpins this paradigm of reality as computation. Quantum computation blurs the line between observer and the observed. Imagine reality as a vast system of quantum gates and algorithms where each particle state, every photon, electron, and quark is capable of carrying out calculations inherently dictated by quantum mechanics. These particles don't merely exist, they compute. They interact, perform probabilistic calculations, and evolve into states of higher complexity. The implications? Everything we thought of as physical phenomena might, at its core, merely be information being processed. At the foundation lies a truly radical idea that the laws of physics themselves can be reinterpreted as computational rules. The equations and constants we've mapped, from Newtonian mechanics to Einstein's relativity and beyond, might be better understood as the operating system of reality. These rules aren't static, they're dynamic processes computed in real time. Quantum mechanics leads the charge here by providing a probabilistic yet computable framework. It doesn't deal in absolutes, but probabilities, calculating myriad potential outcomes and selecting collapsing, to use quantum jargon, the one we perceive. This ongoing mathematical dance is what gives the universe its structure. Look deeper, and you'll find quantum superposition, the astounding ability of particles to exist in multiple states simultaneously. If you've heard of Schindler's cat, you already grasp the concept. On the computational level, this represents parallel processing at its most fundamental. Where a classical computer might handle a computation step by step, a quantum system explores multiple possibilities all at once. It opens a breathtaking possibility. What if the universe itself is performing a kind of massive parallel computation, with every quantum event creating ripples of processed information? It hints at how efficiently reality processes information, beyond what we can achieve with human-made technology. Central to this model of a computational universe is measurement. Quantum mechanics tells us that particles exist in a cloud of possibilities until an observation collapses them into one definitive state. Similarly, a computation doesn't exist merely as a sequence of potential solutions. It must result in an output. Observers, therefore, aren't just passive elements of reality. They're active participants. Every time we measure, we contribute, perhaps imperceptibly, to the computation of the universe's state. But what happens when errors arise in this incredible system? Just as computers are prone to glitches, the universe isn't immune to disruptions. Enter quantum error correction. This mechanism, hypothesized to maintain the stability of reality, may offer insights into why physical laws remain consistent. Let's consider decoherence, the tendency of quantum systems to interact with their environment and lose coherence. Despite this, our universe functions with astonishing reliability. Could it be that inherent quantum redundancy ensures the integrity of reality, correcting errors as they arise and preserving the continuity of existence? Quantum causality adds yet another fascinating wrinkle. Unlike in classical systems, where cause and effect follow a linear chain of events, quantum events operate on non-classical causal structures. Think of it this way: entanglement, one of quantum mechanics' most famous phenomena, creates connections between particles that defy our notions of linearity. Translated to a computational model of the universe, this suggests that information flow may follow entanglement-based relationships. The processing of reality isn't a straight line, but a web of interconnected causes and effects, governed by entropic yet measurable structures. Now, imagine space-time itself, not as a static backdrop against which events play out, but as an emergent phenomenon born from quantum computations. Some theories propose that the very fabric of space and time arises from the relational data processed at the quantum level. This dynamic informational framework would mean that dimensions, distances, and flowing time are derivative features encoded and computed into existence by an underlying system. To make sense of quantum computations in physical phenomena, consider quantum algorithms like Shor's or Grover's. These algorithms are efficient solutions optimized for quantum systems. Intriguingly, these strategies share parallels with natural processes, suggesting that the universe itself might evolve following optimized quantum problem-solving trajectories. For example, the natural selection of particles, states, and interactions may be reflections of these efficient algorithms at work. Which brings us to the tantalizing hypothesis: if the universe is indeed a quantum computer, could reality itself be an intricately coded simulation? The simulation hypothesis suggests that all of existence might function as a programmed model, directed by the constraints of computational limits. These boundaries could, in turn, explain phenomena like the speed of light and the Planck length as the processing limits of this universal machine. The view of the universe as a quantum computational system doesn't just reframe how we understand reality, it opens up new frontiers for exploration. It forces us to reconsider centuries-old philosophical questions in the context of cutting-edge physics and computer science. If the universe is computing reality, then understanding this computation might grant us unprecedented control over our environment, from manipulating quantum states to expanding the boundaries of what we call reality. Ultimately, such a perspective doesn't reduce the awe of existence, it enhances it. Imagine a cosmos alive with ceaseless calculations, a universe mathematically encoding every atom, star, and galaxy. A reality in which you, the observer, are crucial, not a passive recipient of information, but an integral participant influencing the system. If the universe is a quantum computer, then each of us is a variable within its infinite algorithm, connected through entangled threads of information to every other part of this incredible, unending equation. Imagine for a moment that this vast infinite universe is not as it seems. What if everything we experience, space, time, matter, is an elaborate projection? Not a physical reality in 3 dimensions, but a higher dimensional mirage compressed and encoded onto a simpler 2-dimensional canvas. This startling idea is at the heart of what physicists call the holographic principle, and it challenges the very fabric of reality as we know it. The origins of the holographic principle begin with an unlikely source: the study of black holes. Decades ago, Stephen Hawking proposed that black holes emit radiation, now famously called Hawking radiation. This revelation unearthed an unsettling paradox in physics. If black holes emit radiation, they eventually evaporate, seemingly erasing any information about the matter they once swallowed. This posed a fundamental question: does the universe allow information, which is supposedly indestructible, to vanish? Enter the holographic principle, a revolutionary solution to this paradox. Picture a black hole as a 3-dimensional sphere with an event horizon, a boundary beyond which nothing escapes, not even light. The holographic principle suggests that the information about every object that falls into the black hole isn't destroyed. Instead, it's encoded onto this 2-dimensional event horizon. Imagine writing the details of an entire planet on the surface of a sphere. Astounding as it seems, this concept turned physics on its head and became the framework for decoding the paradox. Information wasn't lost. It was just projected differently than we'd expected. Expanding this thought beyond black holes, the principle suggests that our entire universe might operate the same way. Everything we observe as a 3-dimensional reality may actually emerge from lower dimensional information stored at the universe's boundary. It's a bit like watching a 3D video game being rendered on a flat, 2-dimensional disk. What we experience as depth, motion, and complexity is simply a product of vast computational encoding. This brings us to string theory, a paradigm that ties the holographic principle to the very structure of the universe. String theory posits that the universe's most fundamental particles are not points, but 1-dimensional strings vibrating at specific frequencies. More intriguingly, in certain models of string theory, a higher dimensional universe can emerge from simpler, lower dimensional physics, a concept called ADS/CFT correspondence. Think of it as a Rosetta Stone for decoding gravity and quantum mechanics. This correspondence essentially states that a gravitational system in a curved space or anti-de Sitter space is equivalent to a quantum field theory in flat space, which is conformal field theory. The implications are staggering. It suggests that gravity itself, long viewed as a fundamental force, could be an emergent property arising from a deeper quantum reality. This shift in perspective extends to the very fabric of space-time. Some researchers now propose that space-time may not be continuous, but quantized, made up of discrete units like pixels on a screen. Evidence for this could lie in what's called holographic noise, subtle disturbances that may reveal the universe's granularity. High-energy physics experiments and even observations of the cosmic background radiation might hold indirect clues. While these hints are far from conclusive, they ignite a tantalizing question. Could we one day uncover the pixels of space-time? If the holographic principle holds true, it redefines space and time as emergent phenomena, not elemental constructs. This reshapes our understanding of how the universe operates on a fundamental level. No longer would causality, the idea that events have linear, predictable consequences, be a given. Instead, the interplay of quantum information might dictate the unfolding of events, creating a universe where locality and determinism are reimagined. Gravity, too, would step down from its throne as an intrinsic property of matter. According to theorists like Eric Verlinde, gravity could arise from the thermodynamic principles of quantum information, a perspective known as entropic gravity. Quantum field theories, particularly in the context of conformal field theory, provide the mathematical architecture for exploring holography. These theories describe how information on a lower dimensional boundary can dictate the dynamics of a higher dimensional space. By studying these mappings, physicists hope to gain new insights into one of science's ultimate challenges, quantum gravity. Bridging general relativity and quantum mechanics has long been the holy grail of physics, and holography provides a compelling starting point for unifying these seemingly incompatible frameworks. But beyond its revolutionary implications for physics, the idea of a holographic universe raises profound philosophical questions. If our three-dimensional world is merely a construct dictated by two-dimensional information, what does that say about reality itself? Are we inhabitants of an elaborate illusion? What are the ultimate limits of our knowledge? These questions push the boundaries of science, steering us into the murky waters of metaphysics, epistemology, and even existentialism. Consider how this perspective transforms not just the scientific, but the human experience. If reality as we perceive it is a projection, the quest for understanding becomes a search not for an absolute truth, but for the code that orchestrates the illusion. It's a humbling reminder of both the power and limits of human cognition. Our senses, sharpened by evolution, are tools for survival, not necessarily for unveiling the universe's deepest truths. Yet, it's this very drive to question that defines us as a species. The holographic principle also invites us to reconsider our portrayal of science as a field of rigid answers. Instead, science emerges as an evolving narrative, a story we refine with every new discovery. It teaches us that even the most solid concepts, like space and time, can ripple under the weight of new evidence. And if reality itself can be reimagined, perhaps so can the limits of human potential. As we gaze into the depths of the universe, from the swirling mysteries of black holes to the quantum fabric of space-time, the holographic principle stands as a beacon of what science can achieve when it dares to challenge convention. It's more than a theory. It's a testament to the boundless creativity of the human mind. So, where do we go from here? Perhaps the answer lies not in unraveling the cosmos, but in appreciating the profound beauty of the questions themselves. And who knows? The next step in decoding this holographic enigma may already be encoded, waiting patiently on the edge of our comprehension. Reality, as we perceive it, is like a tapestry, intricately woven and seemingly complete. But what if the threads aren't as tightly knit as they appear? What if, upon closer inspection, we realize there are gaps, tears, and unexplored patterns in this fabric we call existence? Today, we're venturing into one of the most enigmatic questions of all time. Can we ever fully decode reality? The answer, dear viewer, may not be as straightforward as you'd expect. First, let's explore the concept of objective reality, the idea that a world exists independently of us. At first glance, this seems obvious. A tree in a forest exists whether or not we're there to see it, right? Yet, attempts to define an objective reality are often challenged by quantum mechanics. For instance, the observer effect demonstrates that observation itself can alter reality. When we measure particles at the quantum level, their state changes, meaning that our act of observing influences their behavior. It's as though the universe only paints the picture of reality once we decide to look at the canvas. This raises an unsettling question: how much of what we call real is simply shaped by the limitations of our observations? We then encounter the limits of measurement and uncertainty, epitomized by Heisenberg's uncertainty principle. At the quantum level, it's impossible to simultaneously measure certain pairs of properties, like a particle's position and momentum, with perfect accuracy. The more precisely we know one, the less we know about the other. This is not a limitation of our tools, but a fundamental property of nature itself. Imagine trying to perfectly capture a photograph of a hummingbird's wings mid-flap. No matter how advanced your camera is, there's always a blur, a reminder that some details will forever elude you. Is knowledge inherently blurred at its edges? And if we were to expand this beyond physics, consider the mathematical constraints on knowledge, highlighted by Gödel's incompleteness theorems. These theorems tell us that within any mathematical system, there will always be truths that cannot be proven using the rules of that system. Think about that for a moment. If the very language we use to decode reality, mathematics, has unprovable truths, how can we hope to build a complete theory of everything? Physics draws heavily on mathematics, and Gödel's work suggests there may forever be gaps in our understanding of the universe. This feeds directly into one of the most contentious debates in science, the interpretational challenges in quantum mechanics. The Copenhagen interpretation posits that reality is probabilistic until observed, whereas the many worlds interpretation suggests that every quantum decision spawns parallel universes. Then there's Bahmian mechanics, which reintroduces the idea of hidden variables, driving quantum behavior underneath the surface. Each interpretation paints a starkly different picture of reality, and decades of debate have yet to reveal which, if any, holds the answer Could they all be incomplete puzzle pieces of some greater truth? Now, zoom out to larger, more tangible systems like you, me, or even our galaxy. Here lies an entirely different enigma, the problem of emergence and reductionism. Reductionism assumes we can understand complex phenomena by dissecting them into their fundamental parts. Yet, emergence challenges this idea, showing how collective behavior in systems can produce properties that aren't explainable by their individual components. Your consciousness, your thoughts, your experiences, they're the product of billions of neurons working together. But you can't fully understand you by studying a single neuron. Likewise, understanding quantum particles doesn't automatically explain why classical reality behaves as it does. The bridge between these two realms remains shrouded in mystery. Can computation come to our rescue? That brings us to the limits of computation in understanding reality. Theoretically, if we had a powerful enough computer, we could simulate the universe and uncover all its secrets, right? Or can we? Complexity theory hints that certain systems are computationally irreducible, meaning no shortcut exists to predicting their behavior. You'd have to simulate them step by step to see the outcome. Think of weather prediction as an example. Even with today's supercomputers, we can't predict weather beyond certain windows with precision. Extending this idea to the universe, could there be aspects of reality that no amount of computing power can decode? A related and even more thought-provoking question arises from the role of probability and indeterminacy. At its core, quantum mechanics relies on probability rather than deterministic laws. For instance, we can never predict with certainty where an electron will be, only the likelihood of its location. If the universe itself operates on probabilities, then how can we hope to map out a reality that isn't deterministic but inherently probabilistic? Are we chasing an answer that, by definition, does not exist? Finally, we must address the philosophical considerations of knowledge's limits. Are these barriers, uncertainty, emergence, incompleteness, epistemic, meaning they stem from our human limitations? Or are they ontic, reflecting deeper constraints within nature itself? Some philosophers argue that science is primarily a tool for predicting outcomes, not uncovering ultimate truths, an instrumentalist perspective. Others, adopting a realist stance, contend that scientific theories aspire to describe objective reality, even if they never fully succeed. This philosophical divide shapes not only how we interpret existing knowledge, but also how we pursue future discoveries. And so, we find ourselves at the crux of the issue. Can we, as finite beings, armed with imperfect tools and incomplete theories, ever fully decode the true nature of reality? The answers, if they exist at all, remain tantalizingly out of reach. It's not just a question for physicists or mathematicians. It's a question for philosophers, computer scientists, and anyone curious enough to peer into the depths of what it means to know. The interplay between quantum mechanics and consciousness has long fueled debates, capturing the imagination of scientists, philosophers, and enthusiasts alike. At the crossroads of physics and philosophy, the quantum nature of consciousness and perception offers a tantalizing glimpse into the mysteries of our universe, our minds, and the reality we perceive. Could it be that the way we observe and interact with the world is fundamentally tied to the quantum realm. At the heart of quantum mechanics lies a concept both bewildering and fascinating: measurement. Unlike classical systems, where everything exists in definite states, quantum systems exist in superposition, a state where particles can embody multiple possibilities simultaneously. Yet when we measure these systems, they collapse into a single state, a phenomenon that defies classical reasoning. Some interpretations propose a link between observation and quantum behavior, though whether consciousness plays a direct role remains an open question. This brings us to the idea of superposition and cognitive states. If particles and systems in the quantum realm can exist in overlapping possibilities, could this translate to our mental states? Consider a moment of indecision where the mind entertains multiple choices simultaneously. While classical thought might view this as a simple mental juggling act, quantum theories propose the possibility of cognitive superpositions, states where the brain, like particles, processes overlapping potentials. This introduces a fascinating concept that the coherence inherent in quantum systems might play a role in our neural architecture, influencing how we think, perceive, and decide. But we don't stop there. Quantum mechanics isn't confined to abstract theories. It manifests in biological systems too. Concepts like entanglement and tunneling, once the domain of subatomic particles, are now seen in processes within living organisms. Microtubules, tiny structures in our brain cells, have been a focus of attention in quantum theories of consciousness. Studies suggest these structures might leverage quantum coherence, enabling information to flow in ways that defy classical explanation. Does this mean our thoughts, memories, and perceptions might, in some part, stem from quantum processes? It's a bold idea, yet one increasingly supported by experiments exploring quantum biology. One of the most intriguing aspects linking quantum mechanics and consciousness is the observer effect. At its core, this principle suggests that the act of observing a quantum system affects its state. Philosophers and physicists alike have speculated on deeper implications. Might consciousness itself, by the mere act of observation, be fundamental in determining how reality unfolds? Imagine a world where reality doesn't exist in full until it's interacted with by a conscious observer. Such a notion challenges our deepest assumptions about how the universe operates. Yet, for all its seeming strangeness, quantum phenomena also hold the key to bridging the quantum and classical worlds. Quantum decoherence explains how quantum systems, interacting with their environments, lose their quantumness, transitioning from a web of probabilities to the definite experiences we encounter daily. This principle safeguards classical perception in a quantumly chaotic universe, ensuring we don't experience reality as a constant, jumbled superposition. The discussion inevitably leads to the intersection of neuroscience and quantum computing. Some theories suggest our brains might operate like quantum computers, leveraging quantum principles to process information. Skeptics argue biological systems are too warm and noisy for such subtleties, but the possibility intrigues researchers nonetheless. Could neural processes bypass classical constraints, utilizing quantum mechanics to achieve feats beyond classical understanding? While definitive proof remains elusive, exploring the brain through a quantum lens may revolutionize both neuroscience and AI. No discourse on consciousness and quantum mechanics would be complete without addressing free will. If classical physics implies a deterministic universe, where every action is the inevitable result of prior ones, quantum mechanics introduces indeterminacy, a fundamental unpredictability in outcomes. Some propose this quantum uncertainty might provide a framework for genuine free will, where decisions aren't preordained, but emerge from a rich interaction of probabilistic states. As we unravel the threads connecting consciousness and quantum mechanics, we're left with more questions than answers, a hallmark of every profound scientific pursuit. Could the mysteries of perception, thought, and reality find their roots in the very laws governing the universe's smallest scales? Or does the quantum realm merely provide metaphors for understanding phenomena that remain, in essence, wholly classical? What is clear is that this dialogue between quantum mechanics and consciousness offers a unique bridge between science and philosophy, inviting us to question, explore, and expand our understanding of ourselves and the universe. And in this pursuit lies the beauty of discovery, not in arriving at definitive answers, but in daring to ask the profound questions. We invite you to keep engaging with these ideas, to challenge assumptions, and to push the boundaries of what might be possible. The quantum universe reminds us that reality is far more intricate, interconnected, and wondrous than it first appears. It beckons us, the conscious observers, to explore its depths and unravel its secrets. What role will you play in this unfolding story of quantum consciousness? The universe is brimming with information. It is encoded in the motion of stars, the vibrations of particles, and the very fabric of reality itself. Throughout the cosmos, information governs the progression of events, influencing everything from the birth of galaxies to the simplest chemical reactions. But what happens to all this information over time? Does it persist indefinitely, or can it be lost forever? Today, we'll unravel how the universe stores information, how it might be destroyed, and the extraordinary implications this holds for physics, quantum mechanics, and even our understanding of existence. To understand the role of information in the universe, we first need to consider its foundations in physics. At its core, information provides a blueprint for how systems evolve. Classical physics tells us that information remains constant. If you know the starting conditions of a system, you can predict its entire future. For example, suppose you understand the position and velocity of a planet orbiting its star. By following Newton's equations, you can determine exactly where that planet will be at any future moment. But while classical processes are information preserving, the same cannot always be said for the quantum world. Quantum mechanics, the branch of physics that governs the universe at an atomic and subatomic level, allows for a different kind of interplay with information. Quantum states, encoded as probabilities, follow a principle called superposition. This principle means particles can exist in multiple states simultaneously, like being both heads and tails before actually being observed. But this leads to a major puzzle. When quantum particles interact with their environment, superpositions vanish, and the system appears classical. This is the phenomenon known as decoherence. Decoherence signifies the loss of quantum information, a process that occurs because quantum systems are extremely sensitive to their surroundings. Imagine a delicate sandcastle built on a beach. Each grain represents quantum information, but even a slight wave, akin to environmental interference, can wash it away. Decoherence is why our everyday reality feels classical, even though quantum mechanics underpins everything. Understanding and controlling decoherence is especially important for building functional quantum computers and secure communication systems. These advances could revolutionize technology, but they depend on our ability to effectively manage quantum information long enough for its full potential to be realized. Beyond quantum mechanics, the flow and fate of information are deeply entwined with the laws of thermodynamics. The second law of thermodynamics, one of the most fundamental principles in physics, states that entropy or disorder in a closed system will always increase over time. Entropy essentially measures how much information is lost as energy spreads out and becomes less useful. Consider the example of ice melting into water. The structured information contained in crystalline ice is gradually lost as the system becomes more disordered. However, the quantum world challenges the idea of permanent information loss. Take Maxwell's demon, a thought experiment that illustrates the counterintuitive relationship between information and entropy. Imagine a hypothetical creature, dubbed Maxwell's demon, who controls the flow of gas particles in a system, separating them into faster-moving, hotter, and slower-moving, colder groups. This would seemingly lower entropy, defying the second law. But here's the twist. Performing this sort of sorting requires the demon to process information, demonstrating that information is intrinsically tied to entropy and energy. Meanwhile, Landauer's principle states that erasing a single bit of information requires energy, confirming that information cannot be handled independently of physical systems. On a grander cosmic scale, the universe itself serves as an incomprehensibly vast record of information. The cosmic microwave background radiation offers a snapshot of the early universe, preserving clues about the conditions after the Big Bang. Similarly, the arrangement of matter, from galaxies to clusters, encodes the entire history of cosmic evolution. Yet, the ultimate fate of this information remains clouded in mystery. For example, does the enigmatic dark matter, which makes up much of the universe's mass, play a role in how information is stored? Or does it act as an impermeable barrier, locking away information we may never access? Dark energy, responsible for the universe's accelerating expansion, further complicates this question. If the universe continues to expand indefinitely, could information be stretched and scattered beyond retrieval? These are some of the most profound scientific questions of our time. But perhaps the most intriguing intersection between information and the cosmos lies in gravity itself. Some physicists believe that gravity arises from quantum entanglement and the flow of information. Imagine space-time, the fabric of the universe, as a woven fabric with threads of information binding it together. If these threads were removed, would gravity cease to exist? This line of thinking challenges traditional assumptions, suggesting that space-time and gravity are emergent phenomena rather than fundamental properties. Such theories aim to bridge the elusive gap between quantum mechanics and Einstein's theory of general relativity. The holographic principle further adds to the intrigue surrounding the universe's informational limits. According to this theory, the maximum amount of information that can be stored in a given region of space is proportional to its surface area, not its volume. This has profound implications for black holes, where gravitational forces are so intense that no information could seemingly escape. However, Stephen Hawking proposed that black holes emit radiation, slowly evaporating over time. Whether the information consumed by a black hole is destroyed or encoded in this radiation remains a hotly debated topic in physics. And what of the universe's ultimate fate? If the universe succumbs to heat death, a scenario where all energy is evenly spread out and no useful work can occur, would all information be lost in this cosmic freeze? Alternatively, the Big Rip scenario, which predicts space-time itself could tear apart, raises equally perplexing questions about the destiny of information. Some theories suggest that information could persist within quantum fluctuations, or even contribute to a future rebirth of the universe in a new Big Bang-like event. The study of information in physics continues to evolve, with ongoing research exploring its role in the structure of reality and the limits of knowledge. Understanding how the universe stores, loses, and transforms information not only deepens our understanding of physics, but may also provide answers to the deepest mysteries of existence. With every new discovery, we edge closer to a unified framework that reconciles quantum mechanics, general relativity, and the elusive role of information. Ultimately, information may hold the key to unlocking the ultimate nature of reality, one bit at a time. Whether through advances in quantum computing, breakthroughs in theoretical physics, or deeper cosmic observations, our quest to understand information marks the next great frontier of human knowledge. The future often feels like a distant concept, but what if it's already unfolding right before our eyes? Advances in technology have always transformed the way we live, work, and think. And now, we stand on the edge of a new frontier, one that holds the promise to redefine the very fabric of human existence, information itself. From the remarkable abilities of artificial intelligence to the mind-bending possibilities of quantum internet, the future of information is a story of relentless innovation and unprecedented potential. To understand where we are heading, we must first examine where we are today. Artificial intelligence, once confined to the pages of science fiction, has rapidly become part of our everyday lives. It's in the virtual assistants that respond to our commands, the algorithms that curate our media, and even in the systems that help doctors detect disease. AI's ability to process and analyze information with speed and precision far surpassing human capability is already reshaping industries. However, the story of AI is only partly written. Its limitations, particularly when it comes to complex decision-making and creative problem-solving, remind us that there is still much room for growth. Could quantum information be the key to unlocking its true potential? The concept of quantum information might sound like it's straight out of a science fiction novel, but it's very real and profoundly exciting. Traditional computers, including the AI systems we use today, process data in binary bits, ones and zeros. Quantum computers, on the other hand, use quantum bits or qubits. Thanks to the quantum phenomena of superposition and entanglement, qubits can represent both 1 and 0 simultaneously. This means quantum computers can process vast amounts of data at speeds that were once thought impossible. Imagine an AI system that could analyze countless variables and scenarios in an instant, solving problems that would take traditional computers decades, if not centuries. This is the promise of combining quantum computing with artificial intelligence. But the possibilities don't end there. Enter the quantum internet, a revolutionary concept that could redefine how information is transmitted and secured. Unlike classical networks, which rely on electromagnetic waves to transmit data, a quantum internet uses quantum particles like photons. Its primary allure? Unbreakable security. Quantum communication leverages the property of entanglement, where two particles become perfectly linked, regardless of the distance between them. Any attempt to eavesdrop on the communication instantly alters its state, alerting both parties to the breach. This makes it virtually impossible to hack or intercept messages, a feature that could revolutionize industries reliant on high levels of data security, from finance to defense. But the potential of a quantum internet extends well beyond secure communication. Imagine a world where quantum networks enable instantaneous data sharing between quantum computers across the globe. Complex scientific calculations, climate modeling, pharmaceutical discoveries, applications that require immense computational power could be tackled collaboratively in ways never before possible. The rise of quantum networks doesn't just promise an upgrade, it suggests a paradigm shift in how we think about connectivity, collaboration, and transparency. Now, let's think even bigger, cosmic even. Could future civilizations harness information on a scale that transcends Earth? It's a provocative notion. If humanity continues to advance our understanding of quantum information, it's conceivable that we might one day achieve a type of civilization that operates on a level that integrates cosmic-scale information processing. There's a concept in astrophysics and theoretical physics called the Kardashev scale. It categorizes civilizations based on their ability to harness energy. A Type I civilization, like humanity, uses only the energy available on its planet. A Type I civilization harnesses all the energy of its star system, while a Type I civilization commands the power of an entire galaxy. Now, apply this idea to information. What if, just as a Type I civilization might harness all its star's energy, a future civilization could use quantum networks to harness and process information on a galactic scale? This idea may sound abstract, but it has profound implications for our understanding of life, intelligence, and the universe itself. If information is the currency of intelligence, then managing information at a cosmic level might allow a civilization to unlock secrets of the universe that we can't even comprehend today. Could this be an evolutionary milestone for advanced civilizations? Could quantum information hold the key to reaching beyond our current grasp of intelligence and consciousness? Naturally, these ideas spark profound ethical and philosophical questions. If we reach a point where AI and quantum computing become interconnected and integral parts of society, how do we balance technological development with humanity's needs and values? How do we ensure that these advancements are inclusive and equitable? The fusion of artificial intelligence and quantum technology is not just a technological challenge, it's a societal one. Of course, technological progress is never without its skeptics. Detractors of AI, for instance, argue that machines could never replicate human intuition, creativity, or consciousness. While it's true that today's AI systems operate primarily within defined parameters, what happens as quantum computing allows AI to analyze and synthesize information at an unprecedented scale? Could we be moving towards an era where AI not only solves predefined problems, but also asks original questions. Such questions lead us to reconsider the boundary between human and machine intelligence. And then there's the question of access. If quantum internet and AI powered by quantum computers become the norm, how do we ensure they don't become tools of exclusion or control? The democratization of these technologies will be critical to their success. If only a handful of corporations or nations wield the power of quantum information, the gap between the haves and the have-nots could widen, exacerbating existing inequalities. On the flip side, a more inclusive approach could level the playing field, providing developing economies with unprecedented opportunities for growth and innovation. The promise of quantum information reshaping artificial intelligence, the emergence of quantum internet, and the futuristic vision of cosmic-scale information harnessing are not merely speculative dreams. They are potential realities rooted in the cutting-edge science of today. And while these technologies are still in their infancy, the speed at which AI and quantum advancements are progressing suggests that they may become integral to the way we understand and interact with the world sooner than we anticipate. The future of information isn't just about faster computations or more secure communications. It's about redefining what it means to live in an interconnected, intelligent, and information-rich world. It's about uncovering new truths about the universe and about ourselves, about what civilizations can achieve when innovations intersect with imagination. As we conclude this exploration, the question we ask is no longer what is the future of information, but rather, how will we shape our future with the information we have? The possibilities are infinite, the questions are profound, and the answers, well, they are waiting in the quantum unknown.